Very welcome from my side. I'm Marcus. I'm from Perception Park. Yeah, today we want to talk a little bit about chemical color imaging and the industrial usage of that technology. Overall, it is hyperspectral imaging based. We are located in Graz, that's in Austria. We are really focused on hyperspectral imaging data processing and only hyperspectral imaging data processing. For us, intuitive user interface concepts is really, really important because the software solution is meant for industrial usage. Also, real-time processing, of course. If you think on a camera system, you want to get the streams in real time, of course. Industrial validity is also a really important point. And last but not least, the system is generic. So third parties can add on their functionality to our framework. Today I want to talk a little bit about our motivation, about instrumentation in general, because hyperspectral imaging might be something new maybe, then methodology, and at the end chemical color imaging. That, I think, is the most important illustration in this presentation, at least for me. It shows our motivation, the concept behind Perception Park. We have in the community of hyperspectral imaging methodology development from science, R&D, also application development, those guys who like to solve applications, and instrument development. What we recognized in the last 10 years is there is a missing interdisciplinary crosslink between these stakeholders, and that's exactly where Perception Park is focused on. Some words to spectroscopy. So when we talk about spectroscopy, we talk about the measurement of radiation intensity as a function of wavelength. So think, for example, on a red object and a green object. The red object reflects in the red range of the spectrum light, while the green apple or object reflects light in the green range. But you can do this also outside the visual range. Think on the near infrared range. And this range is really, really interesting because in that range you get information about molecular combination. That's a chart I like to show you. There's really detailed information. Just to give you the information, there is the information to see what molecules exist and at what wavelength range they absorb light. You see here, for example, H2O, H2O, H2O. This is about 1450 nanometers. This is about 975 nanometers. This is about 1900 nanometers. So by this knowledge, you might have an idea what spectral range could be of interest to solve your application. You can see also here the CH combination, here, here, here. These are typically the molecular vibrations that causes the differentiation of polymers. So polymers are composed of CH combinations, and therefore, if you like to distinguish polymers, then you will find here the absorbance bands. Hyperspectral imaging in general allows us to get spatial resolved spectral information. So it depends, of course, on the instrumentation technology. Standardized is a technology that allows us to get a line scan technology. So for one time point, we get the spatial domain, a line, and in addition, the spectral information. Over time, so maybe you have a conveyor belt, you transport the objects, you get the second spatial dimension. At the end, after a time span, we get a three-dimensional data cube holding reflectance information of the object. Hyperspectral imaging, we call typical hyperspectral imaging if we have more than 100 wavelength bands. This is different than multispectral imaging. When I talk for multispectral imaging, I mean more specialized systems that base on 4 or 5 wavelengths. Of course, they typically are cheap. They are typically reproduced in masses, but of course they have typically no generic usage. Hyperspectral imaging allows spectroscopic techniques because we get the spectral information resolved by wavelengths. Therefore, we can apply spectroscopic technologies. Yeah, it is capable, of course, to do image processing because we have the spatial information too. Yeah, and that can be also temporarily resolved. Okay. Some typical scan technologies available or instrumentation technologies available. This one is the standardized technology. So as I told you, at one time point we capture the spatial domain and the wavelengths, and over time we fill up the cube. Spectral scanning is if we have, for example, a filter wheel at one time point, we get one wavelength. If we rotate the wavelength, the filter wheel over time, we can upsample the cube. There is a new technology named spatiospectral scanning, and also non-scanning technology. Means at one time point you get a two-dimensional image, and behind each pixel a spectrum is located. So one cube at one time point. That's another new technology coming out yet. Some information, short information about data processing. If you think hyperspectral camera is always totally exactly to the next one of the same batch, then I have to say no, there are some differences. So there is a calibration needed to standardize the cameras. By standardizing, typically noise is suppressed, smile keystone correction is done, means there is optical disorder on the image, and we have later on the need to correct that. Defect pixel correction and so on, reduction of nonlinearities. That's typical instrument standardization. And of course, we need also to standardize the setup. What does that mean? Simply speaking, flat field correction, you know, for image processing, for machine vision. The lighting situation can be different. So we have to standardize to the lighting situation to be able to measure something. Some words to methodology. We at Perception Park are data processing oriented. We see 3 basic modules, basic blocks. One are data receivers, like cameras, like files, like network streams. The next one are processing blocks, like data correction, filtering, whatever. And the last one is data transmitters. So camera link output, gigabit Ethernet output, and so on. By building up a graph, so a combination, a sequential combination of different blocks, we can get the complete functionality needed. You can see there are factory modules, there are third-party modules, and there are module groups. So if you like to combine a specific functionality, then it can get a module group and fulfill a higher task, let's say. That's in particular interesting for third-party developers which have a knowledge in data processing aspects, and they like to use their functionality as a part in our data processing unit. That's the user interface. What I want to show you is that by the user interface, the problem is simplified because of the visualization. So such a complex processing network is parameterized by the user interface, and of course results in a differentiation based on chemistry, for example. Such a network is generated by the Perception Studio program. That's the offline tool. That's the tool you install on your PC, and that's a tool that helps you acquiring data, to analyze the data, and to build such a network, for example. If you compile this network for a data processing unit, like the perception system, you are able to process the network in real time. Means for really specific tasks you can generate this network and get it running in real time on the data processing box and output a stream, maybe a color stream or a monochrome stream, what you like. Okay, that's to the methodology part. Next slides, I want to highlight a little bit chemical color imaging. Chemical color imaging is our approach to get hyperspectral imaging technology usable in industry. We recognized in the past that conventional hyperspectral technology is quite a complex topic. If you like to have others, third parties, to work with this technology, then they must be experts in chemistry and so on. Chemical color imaging aims to a really simplification, and it is a holistic approach between chemical imaging and color imaging. The methodology or the configuration process is described like that. It begins by recognizing hyperspectral data. So you get the hyperspectral cube. You also have expectations. You want to separate, for example, as we showed today, sugar from paper, for example. So your expectation is this should be differentiated. And these steps in between have to be performed with different, you can choose different parameters, and at the end you get a perception. Perception is a color image that in best case describes your expectation, but it must not. It can also be that the perception reachable cannot follow your expectations because your expectations are wrong, for example. They cannot be fulfilled. Let's have a more practical viewpoint on that. Here's an example of wood recycling. So it's a typical application you can see in the industrial environment. We have here different objects. The objects denoted by P are polymers, like this, and that's all. Then here are objects denoted by W, this, and this. That are wood. And the aim is, for example, to differentiate the wood from the other objects. You can see here, I have selected here on that point some pixels. Behind these pixels is the spectral information located like is shown here. So this is the wavelength range from 1000 to 2500 nanometers, and you can see the signature. So that are reflectance spectra, and this signature here are absorbance bands and characteristic, for example, for this polymer that is selected. Wood is denoted by blue, is this spectra. You can see there are differences between spectra at least. By applying the extract methodology as first methodology I want to introduce, the user get an unsupervised approach to extract dominant spectral information out of the spectra he selected. So he thinks on the application and thinks what objects might be relevant. He selects these objects, and from the spectra, on the spectrum mathematics is applied, and this results in such color images. You can see in this image the wooden parts are denoted more or are more greenish, while plastics are more yellow. In this image you see the plastics more purple and the wooden in a greenish color. So that could be a first solution for this application, because machine vision guys can use this color information, can classify on this color information very easily. But if you like to have a more aimed configuration possibility, the Correlate methodology might be the best one. In this case, the correlation of spectra to the cube are calculated. So the spectra set from wood correlates at this point really good. You can see it here. The spectra set from that one correlates on that object really good, and so on. So we get here the correlation of spectra to the hyperspectral cube. Simply by assigning this to red, this image to red, this to green, this to blue, we get out this image. And that follows maybe more our expectations, maybe. So we can see polymers are in a bluish color, wooden objects are in a red color. So, but really challenging applications, I have to say, we typically solve with the Correlate, the Constrain methodology. This methodology lets you constrain the color impression which you expect. But don't get me wrong, the color impression you constrain must make sense. So you should constrain orthogonal colors for objects which you think are orthogonal spectrally. So what does that mean? Wood object might have nothing in common with polymer, so they are orthogonal. Therefore, I use orthogonal colors like red, green, or blue. Okay. This one, denoted by U, is an unknown object, but it looked for me, it is like a foam based on wooden material. Therefore, assigned to this object yellow color. Yellow is composed of wooden and an additional component red, which I don't train. And I tell the system, find the proportion of red that might be okay. That's the output image. So this spots, blue spots denote the blue teach, here the green one, and that one is the yellow teach point. What you get is that perception, and that is really interesting yet. Okay, these polymers are really similar. They get blue. The wooden one is green, so that's like we expect. What's interesting is this polymer gets magenta. That means it is bluish and it is reddish. That means it must have something in common with that. That has something in common with that. So I assume the polymer here is also in that one, which is based on wood. So you can also understand and learn with the Constrain methodology. Just paint in the scene here and recognize what results can be obtained. This one is especially really good for extremely noisy spectra. So if you have the need to distinguish, for example, impurities from your good material, and if the resolution is not that good, this methodology typically get out the differences that can be used later on to differentiate the objects. Typically, for example, extract methodology, not, because it is just mathematically finding the dominant trends in the spectra. Okay. Some examples. That's a pharma application. We put 3 blisters of different pills together and scanned the pills. We developed a model to detect these pills, and these pills. You can see it here in blue color. So blue is the active pharmaceutical ingredient. What you can see here is one missing. And here is also one missing. So So the nice thing is you can use NIR technology to look through the packaging and see and can also distinguish between different chemicals beyond or underneath the blister. That's often an interesting application for an industrial field. Here an example of meat investigation. You can imagine that the differentiation between bones, which are white, from fat is not that easy because both are white. Okay, with advanced machine vision, you might have chance to classify, but actually what would we need? I think we need an information channel that transports us the information bone or similar to bone and similar to fat and so on. What we have done here is a characterization of fat in blue color, bone in red color, crystals in magenta, and the meat is in green color. So that could be the output image of such camera, and with machine vision it is then really easy to classify, of course. This is an example from typical sorting, so recycling in this case. Here you can see a stream of polymer flakes. There are polyethylene flakes. Here is one, this is the magenta one, and here are polypropylene flakes, the greenish one. The material speed was 2 meters per second, so it's quite fast. The conveyor belt width was approximately 700 millimeters, and the scan rate was about, I have to look, about 1 kilohertz. So this information is generated in real time, of course, with really low latency, and by applying machine vision, of course, the flakes can be separated by air, for example. Yeah, here are some references. If you like to get a little bit more into detail, you find also an article on the content of this presentation, especially on chemical color imaging, written with illustration and so on. And here are some presentations about marketing, that's modular processing of hyperspectral data, and that's multivariate data processing of multidimensional data. So that's more mathematical one, that's more data processing, that's more marketing, and that's the written thing of this presentation. And if you are, let's say, fascinated about this topic, I can tell you, follow the white rabbit. Next year, not next year, this year in June, we are happy to introduce the first conference on hyperspectral imaging in industry in Graz. So it's the first one that is meant for industrial stakeholders. And yeah, I'm quite sure we will have in June a nice community to discuss hyperspectral imaging in general, so instrumentation, the methodology, and also the application thing. There are a lot of speeches already which are registered, and yeah, I would be very happy to see someone of you in Graz in June. Okay, that's all from my side. Thank you.
Do we have any particular questions?
Yeah, I was the one that spoke at the booth earlier. I've seen this presentation. The question might be one more for STEM imaging, but there was mention of a non-scanning type of hyperspectral imaging. That's what I would be most interested in. Where would I get a kit of hardware from, or is it such a thing as a camera that someone can buy?
Yeah.
Or
STEM imaging provides you all the components, hardware components, as well as software and data processing hardware that you need to do that job. And especially if you have interest on new camera technology, those guys are best to answer that. I can highlight maybe advantages of technologies, if you like, to answer anything to that. What camera technology you are thinking on? This area scan technology maybe, or?
Well, we have an application in mind, not entirely unlike the closing slide there.
Mm-hmm.
So it would involve infrared imaging.
Yeah.
And so we have clients that would be interested in that sort of thing.
Yeah.
We're a company that develops mostly software algorithms.
Yeah, okay.
Preferentially just buys in the hardware.
Of course.
So, yeah, I think it might fall on STEMO.
Yeah, I'm quite sure STEM imaging can give you the right information that there are cameras available with which you can get really impressive results like that one. That's not that, let's say, easy typically to get out such an image, but with a STEM imaging setup it was possible. So that's not that worst image available, let's say.
Do feel free to get in touch with us at STEMA and just say, look, we've got an application, this is what we'd like to do, and we'll talk you through it and any recommendations we have, and get the information on the technology available as well. Anyone else?
Yeah, can I just ask a question about the blister packs with the pharmaceutical applications? Clearly, it's seeing through the material within the blister packs. What sort of limitation on thickness of material can you see through to see the chemical?
It depends on the plastic or the type of material that covers the objects, of course.
In terms of what the differential is to the material that's within it, how big a spectral is through it?
I don't have something to paint here, but I try to describe it without painting. Think on the reflectance spectra of a polymer. In the NR range, you get more or less a good, the absorption is on distinct wavelength position. In between, there happens nothing. Means if you want to detect active pharmaceutical ingredients, and if they are really in between that bands, then you have really good chance to see through. But that is true for polymers. Think on a metal coating. Metal is something that reflects thermal radiation really, really good. So you cannot think that you can look through metal, for example, but you can look through glass, through plastic, and so on. So it depends on the absorption characteristic of the material. Yeah.
Everything done?
You could comment on the spectral resolution.
Yeah.
For the infrared, and then the positive comment on what you achieve in visible way.
The spectral resolution depends on the camera setup, of course, that is used. Typically, the spectral resolution is in a range between. We have to differentiate. There is a sampling, a digital sampling, where you get the information, and there is the true optical resolution. The sampling is often done in a range from 2 to 4 nanometers in the NR range. The sampling, digital sampling. The real optical resolution is in a range dependent, of course, on the spectrograph from, I would say, 4 to 8 nanometers. So something like that. If you are a data processing guy, then it might be interesting to have 8 nanometers optical resolution and 2 nanometers signal sampling, because then you have oversampling. By applying filtering, you don't influence the optical signal and you are able to reject the noise of the sensor. So that's an interesting aspect in this circumstance. Yeah.
But thanks once again.
Thank you.